So I'm taking the next session. I'm going to look at how Waratek's been securing the JVM. But I thought, since we're doing some polls, how many people have actually heard of Waratek? Okay, I'll tell you a little bit about Waratek in that case. So Waratek's a small company. We're based in Dublin. We've been developing a JVM, which, as you'll find out, does virtualization, some other interesting capabilities built on top of the JVM. And fairly recently, we started moving into securing the JVM through this virtualization technology. That's what I'm going to be looking at. So this is a technical overview. It's my first time at this summit, so this may not be very technical for this crowd. So bear with me, but it should be a good thing after lunch, I hope. So I've been in the tech industry for a while, various different roles. Started off doing robotics and process control, then moved into some enterprise software and did some 3D visualization work, all sorts of other bits and pieces. And then I was clearly having far too much fun, so worked with IBM for a while on enterprise software and WebSphere. So definitely I was having too much fun. But then I was doing technical work there, then moved over to, as my colleague said, the dark side and started doing product management and technical sales. Since then I've gone freelance, and now I'm working with Waratek, doing product management for them and again some tech sales stuff. What I'm going to look at today is really what is the Waratek JVM and how it's structured, and a bit about how it's doing what it's doing. What we mean by securing Java and why we secure it and the things that our customers are looking for from us and what we help them with. And then some of the other capabilities, what we've done brings to the party and brings to the JVM as well, and what the benefits of doing those are. Then, time willing, I may be able to get into a demo. I'll see how we're doing for time, and there'll be some time for Q&A as well. So, start off with what Waratek JVM is. How do we define it? So we say that it's a virtualizing VM and that it creates fully TCK compliant virtual containers that are completely isolated on top of the underlying JVM itself. So the picture is trying to illustrate how that works. We can run multiple independent programs, Java programs, in these containers. As far as the application running is concerned, it's the only thing running on the JVM. It's just on a regular JVM. It's very analogous to how an operating system feels running in VMware. It believes it's running on the bare metal, but it's not. It's in a container. So we're containerizing Java. We're licensing our technology from Oracle as well, so we pass the TCK compliance, and we are compliant, and we can call ourselves Java because of that. So why do we put various multiple Javas in boxes? What's the point of doing that? Well, really, it's around controlling those resources and being able to do some neat things like changing the heap that each container's got while the application's running, doing some tricks by telling it how many CPUs it's got visibility of, the bandwidth, and other resources on the machine. That's why we do that originally, and as we've gone through bringing this capability to market, we've heard from people, and one of the things we realized we can also do is secure the JVM through this capability, so we'll look at that in a moment. And of course, because we're managing and looking after all these resources on behalf of each container, we're able to then measure and monitor what's going on and produce metrics around that for people who are interested in just how much CPU did department B use. So people use this information for billing purposes. If we look inside our JVM, it's fairly standard big chunks. You've got the garbage collector. We tend to default to the G1 GC. We tend to be running on top of very large memories. We don't want a garbage collection pause to stop every single application we're hosting. We can host up to 64 applications, and if they all GC pause just because one guy needs to do that and it's a huge memory, then that's a problem for everyone we're looking after. So we favor G1 GC. The class libraries stay exactly the same. We don't tamper with those. They're just brought in en masse. And it's the JIT compiler that's very different. That's where we do all of our work. The JIT compiler's heritage is actually from Intel. It's their dynamic runtime language, or libraries. And we took that. Harmony had it for a while. So we rolled all of that back and forked it at that point and created what we call the DRL v2. Some people sometimes stumble across stale Harmony references and say, hang on, aren't you a Harmony JVM? It's like, no, we're not. That's kind of a side effect of the build process and everything, but we are actually Intel. On top of this, we're building a hypervisor. The hypervisor itself runs directly on the JVM. So we call that domain 0. Logically, it's exactly the same as the hypervisory world from VMware, that kind of environment. So we have this domain 0 concept, something running on the bare machine. And then on top of that, we're creating our containers. And we can go up to 64 of those. That's a fairly arbitrary limit. We've actually pushed it up to several hundred without seeing any serious detriment to the performance of the running applications. But 64 seemed a reasonable number given the size of enterprise applications and the size of machine memories that we tend to stumble across. So I thought I'd look a bit at virtualization and why we've taken the path we have. So we're going to go and explore that for a bit. The world of virtualization really comes in two forms. There's type 1 virtualization. These are not very imaginative names, but there you go. Type 1 virtualization is putting the hypervisor directly on the bare metal and then having multiple operating systems on top of that. And it's the kind of thing you might see in the mainframe environment. They'll have a hypervisory system running directly on the CPU and carving it up for everything else. The other type of virtualization, another imaginative name, is type 2 virtualization, which is the kind of thing you see VMware doing. So there you've got your host operating system running, you're running the hypervisor in an application space, and it's then responsible for creating containers and running other operating systems. I'll dig down a little bit more onto type 1. So what happens in a type 1 hypervisor environment, where we're running a bit like a mainframe type environment, is the guest operating system wants to do something. So of course it makes a call down, goes into the hypervisor. It traps the instruction call. So once it's got this instruction call, it needs to ask a question. And the question is this sensitive? And what's meant by that is this something that's going to cause a problem to any other operating system running in this environment, or something that's going to try and access a resource this particular container does not have access to? If the answer to that is no, it's not, fine, just pass it straight on down to the hardware, let the hardware do its job and send the answer straight back. The operating system just gets on and does its thing. However, if the answer is yes, it's going to grab some memory it's not been allowed access to, then we need to emulate that. We need to say, actually, that memory is just not available. You can't have it, and give the answer back to the OS. So that's kind of how type 1 virtualization works. So we thought, yep, okay, that seems reasonable to us. Let's use that. But when it comes to virtualizing Java, we run immediately into some problems. The first one is that actually doing this trapping and saying this thing's sensitive just doesn't work because the JVM is running in the application space. So immediately, if you try and ask the x86 world, well, is any of this stuff sensitive? It says, well, no, of course it's not. It's user stuff. It's not a problem. But as far as the running Java application goes, there are some calls that will be sensitive. This call here. If one of the containers applications says, okay, I'm exiting, what would the JVM do? It would exit. Everyone else would suddenly go down, which in a production environment is not going to make you very, very popular. So we have to do something about that. We have to somehow intercept that and deal with it. There's also kind of a side problem that we've come across, which is that JEE and every other framework we bump into is actually using a fairly cooperative approach to resources. Every single middleware or app server that I've come across, if you read the box, says, yes, I can run 10 applications on this, no problem. But then you go to the production world, nobody does that. And this is the reason. If one of them starts grabbing all the resources and brings the whole system down, everybody goes down as well, which isn't popular. And really, the last time we saw that sort of behavior in the operating system world was Windows Workgroups and Mac OS 9. So operating systems have moved on and done smarter things, so we thought, well, we need to be a bit smarter for those sorts of environments. So, okay, with Java, how are we doing this kind of type 1 virtualization? How are we managing that? Well, here's how it kind of looks. So we've got the application sitting inside its container, and it starts calling down to the JVM. So we immediately do the same thing. We trap it. We call it an exit transition. It's exiting the container. We grab the method call or whatever it is it's trying to do, and then we say, has the type it's acting on been virtualized? So what do we mean by that? Well, if it was the system type and we're doing an exit, we need to have emulated or done something to make sure that that's not going to exit everyone else. The answer here is no. It's exactly the same behavior. We just let the JVM take the call, get on with it, pass back the answer. But if somebody was calling that system exit, then we go, yeah, okay, we're emulating that type access. So what we need to do is say, okay, this is being emulated, and if a container says, I want to exit the JVM, we shut that container down, but we don't tell anyone else about it. So as far as the, yeah, hi, this question. Sorry, I can't quite hear the question. Why would we want to do this? Okay. Okay, so it's why do any of this in the first place? Yeah, so really we're going to come on to those two to answer that question. It's to do with the securing the application, and it's to do with the efficiencies that we can bring to bear. I will get there. This is kind of the underpinnings. So we've created an interface to this. We've actually published the interface to our JVM, so if somebody wanted to start doing fun stuff with this and having a go at virtualizing multiple applications and maybe find out why, then we've got an API into that. What it's doing is giving you visibility of the type access going on, allows you to emulate different types and behaviors, allows you to share some types across containers, because there are situations where that makes a lot of sense. And then we get to the point where we're saying, is an object sensitive? You can start injecting questions, and that's what we've done as far as security goes. Security, as we said, was the next step. So now we'll get into the whys of some of this. So the first why is it enables us to secure the applications. This has become an extremely hot topic for the Java world increasingly. I think anybody who's been reading the IT press has seen the hits, particularly on the client side, Java's been getting, and on the server side, there's several companies getting themselves in a lot of hot water because of their approach to security or the holes that have been discovered. What we've been doing has been called RASP, which I think is a bit of a horrible acronym, but that's Gartner's choice for you. They called it Real-Time Application Self-Protection. So there you go. Just to take a step back and look at the security world and what's going on in it at the moment and why we fit in where we do, there are two current approaches that are fairly dominant. One is the application itself. Your team are writing an application, they've got the code, then get them to do the right thing, get them to not put holes in the code, basically. That's supported by tools that do all sorts of static analysis of the code, say, hey, this piece of code you've written has got a potential problem, it allows a hacker to inject something, it's not trapping the right things. That's great if you actually have the code, but of course, Java's an OO language, so reuse is predominantly one of the things it does. So everybody's relying on huge libraries where they don't have access to the code, which makes that difficult. It also becomes problematic, we found, when you've got a security team saying, hey, you developers, here's how you should behave. Well, that tends not to go down very well, but there we go. The other side, of course, is in the infrastructure level. standard firewalls, and increasingly we've seen WAFs, or web application firewalls, which are there at the perimeter trying to track what's coming into the organization, requests coming in, and checking are they valid or are they trying to do something nasty. Some of the problems with those, as I've touched on with trying to tell people how they should behave and what they should do, isn't always very popular. And also, as I alluded to, if you don't actually have the code, it's very difficult to do static analysis. We've met some people who are doing bytecode analysis, which really does help a lot. The other thing you tend to get with a lot of analysis tools is huge amounts of output, some of which is valid, some of which isn't valid. So there's a bit of a wading through the results exercise one needs to go through. As we said, it's a bit too cold at the network level, and we say that because all you see is the incoming request. You have no context for it. You don't know what the application was doing at the time. You don't know necessarily what generated it. And in order to build up knowledge around that, you end up having to write extremely complex rules that are tying together a whole context of series of requests, a whole conversation between client and server, which if all you've got is just that crossing point at the edge of the organization, it's very difficult to follow what happened. So people have been looking for something that's somewhere in between, something that allows them to sort of just inject it without bothering the development teams and without causing too much upset in the organization, and something that has much better understanding of what's going on in the application world so it can make sensible decisions and not raise false positives. And that's where we figured, well, actually, the JVM's the right place to do this. The JVM gets to see everything. It can see what's going on inside the application at runtime, but it can also see everything that's coming from the file system, from the network, from the world outside. And as far as the application is concerned, it's fairly transparent. In fact, as far as the world outside is concerned, it's fairly transparent as well. As far as the OS is concerned, the JVM and the application are one running application in the OS space, so it's pretty transparent. And then there we've got that wonderful quote from Gartner, which is just sort of saying they're kind of have been heading in this direction. So what we're bringing to the party with containerizing Java and being able to then, underneath every application, ask this question, is what the application doing valid, or is what's coming into the application valid? Are these two things, monitoring and forensics. We accept that from the get-go. People aren't going to switch this on and say, yeah, if you see something nasty, stop my production. They're not going to do that. What they tend to do is say, let's switch this on, let's gather logs, let's understand what's happening, and then react to it. Or once we've built up trust that you're not going to raise false positives, then we might let you stop things. So monitoring and forensics is quite big for us. And then legacy Java applications. There is lots and lots of legacy Java out there. Most enterprises I've walked into and asked the question, hey, which version of Java are you guys running? The answer is invariably, all of them. And we've even walked into one bank where we found Java 1.0 running on 2 servers, doing something, I don't know what, but they were both going, and they weren't in the company museum, they were providing some business service. So if we look at the first bit, the forensics, we figured that on their own right, the JVM isn't particularly secure. If the JVM's asked to do something, open a socket, speak to a file, it just says, yeah, I'll do that. The security is taking place in the Java layer. It's the security manager that's responsible for checking, hey, who's doing this? Should they be doing that? What's the policy on doing this? It's not the JVM's responsibility to do that, which is okay, but a lot of attacks seem to be based around getting inside the JVM and then setting the security manager to null and then doing whatever the heck they like. So that's a real problem. JNI libraries as well are a particular issue because they can do all sorts of things, and we've seen some attacks that revolve around getting hold of those and causing memory leaks on the underlying machine. So here's where we fit in. We create the container and the application, and we get to inspect every call it makes. And we can inject rules at this point, and that's exactly what we do. we're already saying, is this call going to break containment? Is this call going to upset any other application? So we add the extra question, is this call legitimate? And we also have an option for people to go and containerize the JNI as well by using OS containers in the Linux environment. That's been a request we've had from some people to do that because they don't want this problem of a native library running amok and not just stopping the Java from running, stopping everything else from going as well. So that's what we're doing in security, kind of how that's working. The rules themselves are very, very simple. They're just a single line syntax, but fairly basic. They just say, turn this thing on and here's the parameters. So I don't know if you can read those up there. There's a couple of examples at the top of just disallowing access to /etc. If your application has no business getting inside the configuration directory on your system, then single line bans it. Hi. Yeah. See? Thank you.
When you don't shut up, here's a mic. Yeah, so my question was, do you have any rules that aren't examples of things that you want to do by either, system calls or libc, and should you just be rewriting libc or intercepting system calls or something so that you don't have to have all this additional, like, oh, you touch system.exit and that does something special. Well, all that does is call man exit, exit one, and so you can intercept exit one and do something there instead. So that's my question.
Okay, so if I understood it, it's why aren't we using libc to do this, or so we're already stopping what we call sensitive calls by dint of virtualization. Well, we're not stopping them; we're honoring them as far as the application is concerned. So system exit. We're honoring that call as far as the application is concerned because we close down the container. What we don't do is close down the JVM because there may be other running applications on it.
Okay, so I guess that gets back to my previous question, which is why you have multiple things running on the same JVM, which you said you were going to answer, so I should just let you answer that.
Yeah, I am. That's more of the infrastructure story, and it's much more to do with cost saving and efficiencies, and also being able to change memory at runtime. That's become quite a requirement we've hit. This is kind of the security story, and then we'll get into the other features. Some other benefits of these rules is we can load them live, we can keep changing them, so if you're wanting to, you realize there's a problem with your application, you can just add a new rule, plug it in, off you go. The kind of things we cover with these are really, we're a JVM, so there's a lot to do with the Java language itself, preventing reflection, preventing class loading if we know that there are packages or classes that are deliberately crafted to cause problems. Some throwables, haven't really used those much. File and network access, fairly straightforward things. As I said, we've got a lot of stuff around JNI and process forking. It seems there's quite a few attacks. In fact, if the demo revolves around one where somebody's injecting a dodgy HTTP request, which triggers a process fork, spawns off a small application, which then calls back to the attacker. So we know that can be a problem, and if your application has no need to be starting other processes, why not just say, don't do it? And SQL injection, that's become a huge problem recently. And interestingly, the reason for this isn't databases have got any weaker or something's changed there. It's just that in the last 2 years, toolkits have become available, so you can start doing SQL injection with a very low barrier to entry. It used to be it was something you had to know technically about the database, about the application, do a lot of study, and be quite technically adept to do that successfully, but now there's toolkits, you press the button, off it goes. So in the last couple of years, we've seen a huge ramp up in that form of attack. So that's really how we're doing, what we're detecting, what we're generating forensics on, because we can detect all these things happening and log every attempt to do any of these things. We can also choose to stop these from taking place, but typically we're finding people just want to know that these are happening to start with. I said the other area we're covering is to do with legacy Java. And I said, yep, this chart comes from, I don't know if you can read that, it's from Bit9. They did a study of the kind of back-end Java running for any clients. They studied a couple of thousand different people. They had a look at what they got, and this is what they saw. And this is towards the end of 2013. So Java 8 may be lurking there in that 19% of other stuff. But you can see Java 7, SE7 is there, 10% of it. Huge majority was SE6, and surprisingly a quarter of it, well, unsurprisingly to me, a quarter of it is much older stuff. So there's the whole gamut of different versions of Java out there. It says there were 250 CV alerts for Java. SE6 has got 96 vulnerabilities. Now, a lot of these are client-side. We're focusing on server. So I accept that those numbers tend to be more to do with your desktop environment than your server environment. But nonetheless, I think last time we looked, there were a good 3 or 4 that can impact the server side. So you might ask the question, well, hang on, why have businesses let things get into this state? Why haven't they migrated all of their applications? And really, when we look at that, it's this time to cost thing. The longer they leave it, the more costly it gets. And it's not just a case of taking your code and putting it on the new VM and running it up and checking it. People will do that, but then you find, oh, hang on, we stuffed a whole load of objects in that database, and now we've got to pull all those out and update them as well. And suddenly that library's been pulled, or this third-party library I used to use that doesn't work on that version, and then you get this whole mess to deal with, and it gets more and more costly. And of course, the longer you leave it, the more costly it tends to get. And then people end up looking at their much older Java SE5 and behind, and they're going, well, what's the point? We've only got a bit of this running. We'll just raise exceptions with our teams who are asking us to update and say, hey, let's keep on running these. So it becomes problematic. So what we've done is we've added a facility that we call cartridges, where you can say, well, this container is going to look like SE5. We're going to load the SE5rt.jar. We know what SE5 behavior was for different calls. We know what the spec was for SE5. So we'll just make a container look like SE5. So as far as the application is concerned, it's not moved. It's still on an older version of Java, but actually the host Java is SE7. So it's got the fixes and patches. So even if somebody out there says, well, you're running that legacy third-party application, we know that runs on an older version, we know some attacks for that, and they try and use those, well then, assuming SE7's dealt with that problem, the problem goes away. And of course, this reduces the cost of running your older Java because you can now run it in a modern environment. And the production teams can get on and update and move on with their infrastructure world, whilst not having to get exceptions from policy teams. You can run it on a more modern machine and tick along as you want to. So that's pretty much it for our, yeah, sure.
So you said you're running the actual RT jar from, say, Java 5 here. What if the vulnerability exists in the class library and not in the VM?
Yeah, if the problem exists in the class library, then we'd write the rule around that and say, well, look, you need a set of rules to go with this older version. Because, yeah, you're absolutely right. If the problem was the class library itself, then that needs patching. And the idea of having the language rules, the whole pack around language behaviors is to try and mitigate those. But you're right, I mean, even then, if it's something that's fundamental to the application you're running, you may well be stuck. But this is really to help people just take those older versions and keep running them in modern environments. We've had a lot of people who've said, we're getting a lot of pressure to update stuff and we can't afford it, which leaves them very stuck. Hi.
You actually hold set in this case for testing the customer test because they have to test the application while it was configured.
Yeah, I guess the container looks like SE5, so logically you wouldn't have to. I know most enterprises will say you have to, because you've changed something. So the change team will go, yes, retest. What we're saving on the rewriting, and you're not going to find deprecated things or things that have been pulled. So yeah, I accept that. In most enterprises, they'll say, yeah, something changed, retest it. Someone sneezed near the machine, retest it. Yeah, it goes like that.
What are you doing about native libraries of JNI in this situation? Does each container, if the application needs JNI, then get its own copy? Or?
Right, so for JNI, what we've done is we've introduced 3 different rules around that. The first rule is if your application has no need to use JNI, then it's banned. You turn off JNI, and if it tries to make a JNI call, it gets an exception. JNI not found, whatever. We then have what we call the whitelist and the grey list. Whitelist says these are the JNI libraries you're allowed to access. The list contains the path and the MD5 checksum for the library, and those are the only JNI libraries it's allowed to call. Actually, this requirement came from a bank who said, we want this for the libraries we wrote. We know what's inside those libraries. We understand them very well. We want to be able to call them, but only call them. And then, of course, if somebody tries to call another library, they get an exception. The grey list is the one that does the containment, and that was, they said, well, we've got this whole bundle of libraries that third-party applications want us to run. We don't have the code for those, but we have to run them. And it works in exactly the same way. Only the listed libraries for that container can be called, but the libraries are run within an OS container. I will say the downside of that is that that's much, much more resource intensive. Running that container adds overhead, way more than the whitelisting does. But it's there.
But every app that has if every app listed the same whitelisted library, you'd load n different versions of that library?
We would load, if they were pointing at the same library, we would load the same library, but give them separate, I think we give them separate references. I should have said up front, I did. I'm on the product management side rather than the actual development side, but I can certainly check. I believe we load separate references to them, but I'd have to check that to be 100% sure. Yeah.
To enforce all these rules, you have to monitor basically at least every call,
Yep.
or library call.
Yep.
So how do you deal with the compiled code in the init? How do you enforce the rules here?
Right, so the rules are getting called by our hypervisor. The application's inlining and its optimization all happens up front, and we do that because we're running multiple applications. As we load the application, we'll optimize the whole thing, and our JIT compiler underneath is doing that, and one of the modifications we've made is to the class headers, so each class has got also a container ID as well, so we know where they live. And then at runtime, the libraries, or the rules rather, are being applied by the hypervisor before it actually gets down to the calls to the JVM itself. And if we're compiling stuff, we've already brought that up. It's the instantiation of the object's already happened. So it shouldn't be impacting any of the compilation. It's just the runtime side. Does that make sense? Yeah, I mean, because we're already asking questions every time a call's made, there's already some overhead, because we're virtualizing, and virtualization has a cost. But actually, it's a fairly light cost. I did do some transaction testing with one customer. We did, what was it, Konacart, which is an open source e-commerce suite. And we did some transaction testing with that, and we found that, well, at first we thought we'd set things up wrong because we had a standard VM and RVM running on 2 separate machines, remote from the test client. and we were getting the same results. So we thought, well, hang on, if we pointed them at the right machines, what's going on here? But yeah, you do see the overhead if you run the test client on the same machine. And then you start seeing, hang on, we're maybe 10%, 15% slower because we're doing this extra processing. But introduce network latency, and suddenly you're going, hang on, I can't see the slowdowns. Yes? So, sorry, the virtualizing API we've got is purely if you want to start making containers behave in your own peculiar ways. We don't require any change to the application code. We've always said if we require a developer to change their code, then we're broken. So, let's see, time. Yeah, we're doing good for time. I'll come on to the sort of underpinning, well, why did we do this virtualization in the first place? The security's been a hot topic for us, so we've done a lot of work on that. So the other reasons we did this really are twofold. One is driving density of Java workload and getting more efficiency out of the machine. And if you can get more efficiency out of your machines, then they're cheaper to run. It's exactly the same premise that VMware have built their business on. The more stuff you can run on a piece of metal, the more you're saving money. Fairly straightforward. The other is we do actually introduce some stability, and I touched on that JEE has this shared resource approach, which can be problematic, so we'll take a quick look at that as well. So we do help with some stability. So this was a test we actually did with a customer, and we've actually found out we can go further than these test results. What we did was we took standard JVM. It's a fairly simple bake-off type test. It was actually with Korea I did this. Ran up 3 instances of JBoss with their application, allocated a gig to each of them and warmed them up. Got the application up and running, nice and warm. And then said, well, okay, if we allocated 3 gig to our JVM, put the applications in containers, and looked at how much heap they're actually using, what could we do? And theoretically, how many more could we cram on the machine? And the answer was, well, we could get 10 more on the machine, which is fantastic, and still have some memory left over, so that if you asked each container how much memory it's got, they'd all say, about a gig. Now, that drives up a very large density. That also drives up the risk that one of them is going to go out of memory at some point. So in production, would I go that far? No way. I wouldn't recommend doing that level of density for an application of that profile. But certainly, we could double what they were running on the machine without too much risk. With certainly an acceptable level of risk in terms of how people overcommit memory in existing virtualized platforms. In fact, we did some work with Accenture, and they said with their standard Java platform that they go around recommending, they could get up to ×6 density, which is, again, I don't know if they did the risk analysis, but that was kind of good to hear. So how do we start driving that up? Well, I guess that's a picture everyone here is very familiar with, so I won't bother going into too much detail on that. Just to say that, when we look inside on a lot of applications, they tend to be running just a fraction of what's been allocated. In fact, one site we found that they were only using 40% of the heap memory everyone was allocated. So you might ask, well, hang on, why are people allocating such large amounts of heap and then only using a part of it? Well, if I go to most Java developers and say, how much heap does your application need? They're going to come out with quite a large number. They'll say it needs 2 gig. And then if you think about why did they say that? Well, on a Friday afternoon, when everyone is trying to get home, wants to leave for the weekend, they all sort of submit transactions. They're all hitting the machine really hard. Friday afternoon, wallop, it's under load, it needs 2 gig. The rest of the week, it doesn't need anything like that. So why did they allocate 2 gig? Because they can only shut down and restart their JVM to change that memory, which is not very efficient. If we can change it at runtime, suddenly the paradigm's slightly different. you can ask the developer, well, how much do you need on average? And then the answer is very different. Then the answer is, well, I only need half a gig. But maybe on Friday afternoon, I need another 1.5. Okay, we'll set you up running on half a gig, and we'll make sure there's a reserve around that we'll share between you and a few other people. And so long as we put heterogeneous applications on a server, we can probably do that. Right? Clearly, if they're all peaking and bursting at exactly the same time in lockstep, possibly like Netflix might, then okay, different story. But in enterprise, where you've got all these different business services running, you can start mixing and matching. There's some other tricks we can do as well. If we've got various objects that we've allocated across, well, for a start, our JVM is spread across multiple containers, so you're amortizing the cost of the JVM running in memory. You can do the same with some of the code cache, not all of it, but some of it. And you can do the same with the permgen. You can just add a counter to say, well, how many containers are looking at this object? Because it's shared across all of them. It's an inert object. It's not introducing risk. We're not emulating it. We're not having to force integrating separate instances, so we can just create the one and reference it. And then when it comes to the heap can be smaller. So I think, oh yeah, there we go, memory, amortize that. We can share some of that. Share that, and we can make the heap a bit more efficient, as I said. We can start asking, on average, what do you need? And do that, and keep some in shared reserve. So that's how we start driving up density on machines, which means that out of the same box, you can maybe get twice the Java workload. And that's when people start going, well, that's great, because now I can reduce my operational costs. And you know what? Next time I'm looking to buy kit, I can start reducing my capital costs as well. Which, if you're a small shop, doesn't make too much difference, but at scale, that suddenly starts really kicking in, and people start going, hang on, that's saving me huge sums of money each time round. There we go. Yep, can change the heap. Just to sort of start digging a little deeper onto that and start looking at how we introduce some stability as well. For example, if we had some existing JVMs, we've got 4 of them running in this picture. Again, maybe only using up to, I think one of them there, 60-70% of the heap. But between them, I guess they've got their 4 gigabytes of memory between those 4 applications. But in this picture today, if application on JVM number 3 says, actually, I just need to go allocate 205 meg of memory, they're going to get an out-of-memory error, which seems to us really crazy, because if we look at the rest of the picture, there's over a gig of memory here. So why is this guy constrained? Why is he going to run out of memory? That shouldn't happen, really. So if we were to install them in containers with no controls, no limits, just kind of install them in separate containers but allocate the 4 gig, now that's available to anyone to go in and get. So this time container number 3 rather than JVM number 3 needs 205 meg of memory, gig of memory. Fine, it's there, just go get it. We'll just share the whole lot across everybody running on the box and just let them go and get it as they need it, and starts making a much more stable picture. To go back to some of the other benefits and why we're doing all of this and the density thing, that starts kicking in if we start controlling this picture. This is with no controls at all. If we control the picture, what we're saying here is that we've given everybody in their container 20% overhead. So this is container number 1. That's what it's currently using. This is its overhead. That's completely dedicated to that container. It's private. Yet they've got a shared pool here, so they can all dive in, utilize that pool. Same for these guys, but it allows us to carve out 2 more containers. So again, we're driving up the utilization of the box, we're getting more workload through it. And just to go to a more extreme picture that we might see in dev test, certainly in a test environment, as long as you're not load testing, you could do this. You could already squeeze these guys, so they've only got a part of what they need. They've only got 60% of what they need. They're forced into using the pool, but we've doubled the workload, doubled the number of tests we can run. Hi.
Are you running a separate instance of the garbage collector for each container?
No. We're using one garbage collector, and we use the G1GC because of this picture, because we don't want, if this was 64 gig of memory, and there was a pause because one container needed collecting, that would kind of be cruel on everyone else.
So when you say that you have a container, you have an amount of memory, you have memory for it, when it reaches that memory, do you trigger a collection for the entire machine or just for that container?
Well, with the G1GC, it's region-based collection, so it's already split the memory into lots of small regions, and it's continually collecting in the background, as I understand it. It'll, as that container is filling, it will be part of the scheduled garbage collection that's going on anyway. So there's no huge pause, but there's lots of micro pauses.
Not pause is the question. It's when do you trigger the collection? When do you start?
That's a good question. I would probably need to refer to our dev team to get you the technically correct answer. So I don't know. But I can ping me and we'll definitely let you know. So anyway, that was the last example I was going to go through, just to say that's what we do. Any questions, any further questions? Yes?
It seems like with VMware and traditional hypervisors, you've got so much hardware support built, baked into the CPUs these days, and it doesn't seem like you guys can take any kind of advantage of that with this setup. Doesn't that put you at like a real disadvantage versus like a more traditional hypervisor setup, where you just have a couple different OS images and then
Kind of, but we do use some of the features from the C groups on Linux. So we can, if that's not available, you're right, we don't get any of the advantages of the built-in stuff available. But if we're using the C groups library and that's present, then we can start taking advantage of some of that and start using fine-grained CPU allocation and thread controls and all sorts. So some of that's available to us.
most of the advantage that you're seeing is coming from footprint.
Yeah.
So if, say, this is the standard like OpenJDK, just have like maybe more performant, like adaptive sizing of the heap, and we were somehow able to like use shared memory to amortize the, like static data that's the same across all the different instances. We would have
That's kind of some of what we're doing. Yeah. Okay, I better shut up now. So thank you for listening.